Okay, in this video we're going to talk about some special formulas that show up in factoring. So I'm going to start by just solving this the way we've talked about already. This is a quadratic where the lead coefficient is 1, and so the only thing I should do to make it look like all the other ones we've done is write it as a trinomial. So write in the implied plus 0, so that b is 0 and c is negative 9, and then use our method to say p times q is equal to negative 9, and p plus q is equal to 0, and then look at some possibilities of how that could happen. So products that spit out negative 9 are 1 and minus 9, 3 and minus 3, 9 and minus 1, and that's it. And so the only ones that add up to 0 are 3 and minus 3. So that means your p and q are 3 and minus 3. And so this should factor as x plus p, x plus q, where p is 3 and q is minus 3. Okay, so this is an example of a formula that we're going to see a lot. Whenever we have a square minus a square, it turns out it's going to factor exactly this way. This is x squared, this is 3 squared. It turns out it factors as x plus the 3 and x minus the 3. So when we happen to see a square minus a square, we can factor it as the sum of the two and the difference of the two original numbers. And because of the left-hand side, this formula is called the difference of squares, because we're subtracting two squares. Okay, let's look at another example. Factor 4x squared minus y squared. It's a little more complicated, but I think it is a difference, and both the beginning bit and the ending bit are squares of something, because 4x squared is the same as the quantity 2x times itself, and y squared is the same as y times itself. And so we've been able to rewrite 4x squared minus y squared as a square minus a square. So it has to be, what is the number a? I can't just say 4x is a, because order of operations doesn't work that way. This is not a single number being squared. Only the x is being squared. When I rewrite 4x squared as 2x, the quantity squared, then I can say, okay, that's my number a, y is my number b, and so according to the difference of squares formula, we're going to add the two, we're going to subtract the two, and those will be our two factors. Okay, so that's our answer for factoring 4x squared minus y squared. Let's try one more. Factor w squared minus 5. At first glance, this looks like this is not a difference of squares, because 5 is not a square. But maybe we can finagle it. It does look like a square minus something, and this something is just a number. If I can rewrite the number 5 as something squared, then I'm in business. I could do the same thing I did in the last problem. And the idea here is, when is 5 equal to mystery number squared? Well, if you take a square root of both sides, the question mark, the mystery number, is going to be the square root of 5. Or, using a formula we talked about in the exponent section, the square root squared spits out the number you started with, assuming there's no negatives involved inside, which there's not. And so I guess w is my a, and square root of 5 is my b. And so we add those two numbers, we subtract those two numbers to get our factored version. W plus square root of 5, w minus square root of 5. Okay. Let's try one more. Something to be aware of is that we're going to have to combine all of our methods that we've done before. All the examples I've shown you in the videos have been use a particular method, we use that method, we're done with the problem. We also need to be able to spot when are we supposed to use different methods, and sometimes we'll need more than one. So in this problem, notice that there's a 3 and a 12, and 3 and 12 have something in common. They're both multiples of 3. So there's a common factor of 3. So before I do anything else, I should probably look at that. It turns out the greatest common factor is the simplest of all of our ways of factoring. So if it applies to a particular problem, we should do it first so that we get a simpler problem. So I can rewrite this, factoring out the greatest common factor of 3 as 3 times x squared minus 4. So that's one step using the greatest common factor approach. But now this is a square minus a square, x squared minus 2 squared. And so I can use this formula with a is x and b is 2. And so it's 3 times x plus 2, x minus 2. So be aware we're going to have to use sometimes lots of our formulas one after another after another. Okay. I wrote in the title of the video special formulas. There are some other ones I want to mention briefly. The one I just put, difference of squares, it comes up so often and is so time saving when you actually use it. This one is definitely worth memorizing and using on a regular basis. The other ones I'm going to talk about, sometimes they're useful, not really the end of the world if you forget them though. So the next formula I want to talk about is if you have a square plus 2 times a times b plus b squared, that ends up being the same as a plus b times itself. So keep in mind that a square in this case means a plus b times a plus b. There's a variation of this. If it has a minus sign in the middle, it's actually going to have a minus sign on the middle term. Okay. So these two formulas are known as perfect squares, since the right side is just a single number squared. So times that this would be useful is when you happen to see a polynomial that is exactly in this format, then you can use that formula. But that's so specific, I don't know that that's something that I want to like check every time. Like if you tell me x squared plus 6x plus 9, is it worth the time to check if that formula works? Or should I just use our method of factoring quadratics with lead coefficient 1 and just try and find a p and a q? Probably that's what I would do, is just find a p and a q, and it should work. We should end up with x plus 3 and x plus 3. Alternatively, if I happen to spot that this is the same as this formula for a is x and b is 3, then great, I can use that formula. But it probably would have been quicker and easier, or just as easy, to just factor normally. Okay. The last formula I want to mention is when you have a cube plus a cube. It factors in a strange way. Like so. And if you have the cube minus the cube, we get something similar, where if you look at the two formulas, the signs here are the same, and the signs in the middle are the opposite. Okay, anyway, so if we happen to see a cube minus a cube, there is actually a formula for cube minus cube. Here's what they are, in case they show up in your homework. I'm not going to expect you to memorize any of these four on a test. I will expect you to know this one just because it saves time and you're less likely to make errors if you use the difference of squares formula. Those four, these two are kind of very specific to certain problems, so I'm not worried about them. And then these two, we can solve the problem in another way. Okay, so mainly we're worried about the difference of squares. One other thing I wanted to mention, kind of a common point about the cube plus cube, cube minus cube, and the square minus square is if you look at the right hand side of any one of these, it looks like you should FOIL and have a whole ton of terms. But you're only seeing a squared and b squared. And the reason for that is when you FOIL, you're outside a times negative b, and you're inside b times a. They end up being ab and negative ab. They're exactly the same with the opposite signs. They end up canceling. And the cubes end up, the same thing happens. That's why there's kind of some weird, some positives, some negatives in the middle steps. Is they're set up in precisely a certain way so that all the middle terms end up canceling and all that's left is just your a cubed and just your b cubed.